Hi everybody, welcome back to the section 2.3. In this video, we're going to be solving a linear equation. So here is a linear equation for us in example 1, 2 times dy over dx minus 6y equals 12. And so the first thing we need to do is make sure our dy over dx, our derivative here, is naked. It's by itself. Okay? So what we need to do there is get rid of that 2, clear it out. So I just need to divide everything by 2 to make sure this dy over dx is naked. So we like to call that step 0. Okay. And so step 0 is divide by 2, meaning get dy over dx naked. All right. And when I do that, what I get is just dy over dx minus 3y equals 6. So we do this to get the linear equation into standard form so that we can start the process of solving. Because what does standard form look like? So if you could recall standard form, it's dy over dx plus some function of xp times y equals some function of xq. And so if we look at our equation now, -3, well, that's my p of x is being multiplied times y, and 6 is just my q of x. So luckily we just have constants here in this problem. Makes it a bit easier to work with. Uh, Sometimes we'd have functions, but here luckily we just have constants to work with for our functions of x. And so we're now in standard form, so we can start the process now. And the first part of that process is that integrating factor. So step 1, calculate the integrating factor. Okay, so we're going to calculate the integrating factor, which is also known as mu. So the way we do that is mu is e raised to the integral of that p of x function. So we need to integrate p of x, and e is raised to whatever that integration is, and that's our mu integrating factor. So luckily we have constants, so it's easy to work with. So this would just be the integral of 3 dx. That's what our p function is. And that would just be e to the negative 3x. And then we'll account for the constant c. Okay. So we can use properties of exponents and powers. We could split this up to be e to the negative 3x times e to the c. And e to the c is just another constant, so it's c e to the negative 3x. And this is our integrating factor mu. So we wrote c, we accounted for c, but in the future, we don't need to account for c. Okay, we'll see why in a second, but in the future, when you calculate your mu, you don't need to account for this c. Okay, but let's see what happens, why that's the case in step 2. So step 2 is multiply both sides by, or multiply both sides of the differential equation by the integrating factor we just calculated. So what I'm going to do is take my mu, c e to the negative 3x, and I'm going to multiply it by both sides of my d e. So on the right-hand side, it's just 6. Okay. So what we do now is let's observe this C. So I have C on both sides here. So what would happen if I just divide C to both sides? Well, they will just cancel out on both sides. So including the constant is a bit redundant here. It just goes away anyways. It's just an arbitrary constant. So we don't need to really write that. Okay, so we don't need to write the constant, but let's go ahead and distribute in this e to the negative 3x while we have this written out. So what this becomes is e to the negative 3x dy over dx minus 3y e to the negative 3x equals 6 e to the negative 3x. Okay, so this is what we have now. This is our differential equation. We're still trying to solve it. We're still trying to get it to a point of integration. So there's a nice little neat trick here that we do. But before we see it, let's rearrange a couple terms that'll make it easier to see. So let's rearrange it like this. E to negative 3x dy over dx. Let me rearrange this middle term to look something like this. I'm going to put plus, going to put parentheses, but I'll rewrite it like 3 e to negative 3x, and then I'll keep that y here at the end, just all being multiplied, just moving it around. 6e to negative 3x. So I'm really only rearranging that middle term. So why do we rearrange it? So when we do this, there's a nice little trick, okay? So here I'll say like a nice trick to do. What we can do is recognize that the left-hand side is a derivative of a product. So this left-hand side, I'm going to erase this, but this left-hand side is a derivative of a specific product. Okay, and what that entails is a product rule, which is f g prime plus g f prime, or however you like to write it. But let's look at this left-hand side. So e to negative 3x, the derivative of e to negative 3x would be on the right-hand side, excuse me, on the over to the right, would be negative 3e to the negative 3x. So that's its derivative. And the derivative of y is going to be dy over dx. So essentially, we have a product rule here. We have f, we have g prime, we have f prime, and we have g. So this is a product rule. And so what is this the product rule of? Well, it's a derivative with respect to x. That's why we get dy over dx. But it's a product rule of the product e to the negative 3x times y. So here I'll say this is the derivative. So that's the derivative of e to the negative 3xy with product rule. So that's a nice little trick that we do for linear equations. So you're going to be doing this for every single one. Okay, so it's not just the specific example. This is always the case. At least for first order in this course, okay? Okay, so that's the left-hand side that we've taken care of. The right-hand side is still the same. We haven't done anything with that. But step 3 now, we want to integrate. Step 3, integrate both sides. So here I have d over dx e to negative 3xy equals 6 to negative 3x. And so I want to integrate both sides. So what would happen if I integrate both sides? Okay, the right-hand side, that's normal. That'll stay the same. But here, the integral of a derivative, well, that just cancels out. The integral and derivative cancel out. They basically undo each other. Okay, so what I'm going to be left with is just e to the negative 3x y. And so now I need to solve for 6e to the negative 3x, that integral. But we could go out to the side and figure that out if the mental u sub is a little unclear for you, but it's a good practice to try it out. So here I'll say like mental u sub. So the integral 6e to negative 3x dx. We could do u equals negative 3x, du is negative 3 dx. So we'll have du over negative 3. And so this becomes, I'm going to take the 6 out, integral of e to the u du over negative 3. If we take out the negative 1/3, it becomes negative 2 e to the u du. And then negative 2 e to the u plus c. Then we plug back in what u is, 2e to negative 3x plus c. Okay, so that is our mental use of, but we could be able to do that in our head once we recognize it, but it's good practice to try it out if you need it. So what we get here is is negative 2 e to negative 3x plus c. And we want to solve for y, so we'll divide e to the negative 3x to both sides. So it'll be like negative 2 e to the negative 3x over e to the negative 3x plus c over e to the negative 3x. This works out well. The e's to the negative 3x cancel out. We can bring up our negative exponent to be timesing the c. So what we get is c e to the 3x minus 2. And then that is our answer. Okay, so as you notice, solving a linear equation using this method takes a bit of steps and takes a while. So you just gotta be careful you're having the right integration factor. Okay, and a key indicator here is that um, you know, if it's not a product rule, something went wrong. Okay, so if there's no way that you're able to get a product rule out of this setup, then you're doing something wrong. You should always get a product rule when doing this. Hopefully you can recognize them, but if it's not getting there, then maybe your integrating factor is wrong. Maybe you didn't isolate dy over dx, but that's always a good tell. Okay, but that's it for this video, and we're gonna try a couple more, but I'll see you in the next one. Okay, take care.